he moved.
It's my great pleasure to introduce Professor Martinez and one of the organizers. And actually, this workshop originally started from Martin and children, and the idea comes from them. And then after that, probably children and secretaries, everything, and organized very nicely. So in any case, he is going to have 2 lectures, and one lecture this afternoon. Title is Gamma Class and TT Star Real Structure. Lecture 1 is Phenomena.
Thank you. Yeah, thank you very much. So I'm going to talk about the gamma class, but I'm not a specialist on this. So I want to just try to explain some history and, well, some things to do with the real structure, but that will be in the second lecture. So first of all, today is basically just motivation. And I should start with some history. Well, the idea probably you know is we have some manifold or variety or maybe some quantum field theory, some object, and in the case of a manifold, we have something called in the case of, let's say, a complex manifold or a Kähler manifold, we have the quantum differential equation. QT is quantum differential equation. And then, at least in special case, this will be an ordinary differential equation. And then it's an elementary, there's an elementary idea of monodromy, monodromy data of this differential equation. And from the monodromy data, we try to extract, or we can extract some numerical data, some numerical information about X on X. And I'm not talking about Gromov-Witten invariants. Of course, Gromov-Witten invariants are numerical, but they are related to the solutions of the differential equation. So I'm not talking about that. It has to do with the monodromy. And for example, the gamma class. So this kind of information, which is basically going to be topological information. And there's a famous conjecture called the Dubrovin conjecture related to the gamma class. And the Dubrovin conjecture is a geometrical interpretation of the gamma class, basically. So this is going to be related to the Dubrovin conjecture, which is related to homological mirror symmetry, and so many interesting things involved here. Okay, so the starting point, this kind of thinking everybody knows, I think, came from physics, 1990s, 1980s maybe. And mathematically, there are some nice, very fundamental articles by Giventhal and by Dubrovin. Well, let me see it, Kontsevich. In the proceedings of the International Congress 1994. So there are 2 short articles which are very somehow inspirational. And then another inspirational article by Dubrovin in the following ICM, 1998. So, of course, the Dubrovin conjecture is from this time. So to explain this, well, of course, there are many things to talk about. I mean, this is already more than 20 years ago. Well, 30 years ago. And a lot of things have happened. But I just want to illustrate the idea, and I'm going to do that by focusing on the most basic case. So to illustrate the idea, this idea, I will focus on the case of quantum cohomology, small quantum cohomology of projective space. So this was one of the first examples. Actually, I'm mainly going to talk about the case n equals 2. Well, n equals 1 would be the simplest, but it's a little bit too special. So n equals 2 is not so bad. It's possible to write on the blackboard. More than that will get very complicated. So I will probably just focus on this. And this is, of course, a Fano manifold, not a Calabi-Yau manifold, but, well, as you know, quantum cohomology of Fano manifolds, quantum cohomology of Calabi-Yau manifolds are related when you take hyperplane sections, complete intersections. And in fact, it seems that the whole story is somehow reflected. I mean, it's different, of course, for Calabi-Yau manifolds, but something like the gamma class and mirror symmetry. And for Fano manifolds also, there's a gamma class and mirror symmetry. So many things conceptually might apply to Calabi-Yau manifolds, but I will just focus on this Fano manifold. So I should write down the quantum differential equation, which I'm sure everybody knows. Quantum differential in this case is this ordinary differential equation. So that's the scalar form, and I could write it as a first order matrix vector equation. Like this. Y, right? So y is a vector y0, yn. And well, y, of course, is a function of q. Q is a complex variable. Yes, well, it's good to establish notation. Q is a complex variable, and my notation around D actually stands for this. So Q d by dq. And lambda is a parameter, right? Lambda is a constant. It's the spectral parameter of integral systems, which some people write with a h bar. Some people write as 1 over z. Probably there are other ways, but lambda is a constant. And we have an ordinary differential equation for the function y. And it
not 1 over.
sorry?
Maybe just z.
Yeah, maybe just z, yes. Is that what you meant?
Even the form is reversed.
Yeah, people, of course, people use different choices. It's very annoying. So I'm going to try to be very consistent in this lecture. So please, yeah, feel free to improve the notation. But I would like to use Q as a variable for the quantum differential equation.
But it is lambda, so it's completely different from ours.
Maybe so, yes. However, I'm going to fix lambda to be 1. So in this lecture, lambda will not play much role. Usually lambda is important for me, but it will be 1. So it doesn't matter what we call it. Okay. So it's a linear equation, so you can solve it basically not explicitly, but you can. There's a vector space of solutions, multi-valued solutions, and they all extend. Well, of course, q equals 0 is a bit problematical, right? There are singular points. So we have of course singular point at the origin. This is a regular singular point, and well, I'd like to also consider infinity. So this is an irregular singular point. Yeah, that's of course where the problems start. It's an irregular singular point, but basically just these two singularities, and the one at the origin is regular. So we are really working on C star, and the solutions, because they're multi-valued, they're defined on the universal cover of C star. Okay, so we are really going to be working on the universal cover of C star some of the time. And yes, so why is it quantum differential equation of CPN? Well, because the vector space, Cn, we are regarding this as the cohomology, the cohomology of CPN. Right, so that's why it's a quantum difference. And this is, of course, with complex, I want to always use complex ODE theory, so it's a cohomology with complex coefficients. So that's the example, which is a well-known example. Now, let me draw a picture over here. I will draw it very big so that everybody can see it. So I want to write conceptually how this monodromy data will be treated. So monodromy data, well, for example, there's going to be 3 kinds of monodromy data. 1, 2, 3. Oh, sorry. And the first one is simply the monodromy matrix. Right, so you have a singular point at the origin, and so when you do analytic continuation around the singular point, you will get monodromy. So the analytic continuation for the monodromy data, for the monodromy matrix, will be around Q equals 0. Well, it could be around Q equals infinity because they are the same, right? We're talking about the sphere with 2 points removed. But anyway, around Q equals 0 or infinity. And then the numerical data which comes out of this, well, maybe I should call it topological data, because it's topological. And it's e to the 2 pi I x. So I will use this notation. So x is a generator of the second cohomology. Okay, so that's because this matrix, you see, what happens at Q equals 0? Well, when Q is 0, the residue is, yeah, I mean, so I should divide by Q, right? So I divide by Q. This becomes a 1, this becomes 1 over Q. So the residue is basically this nilpotent matrix, which represents the cup product with the generator. So that's why I write the numerical data, the monodromy, in this form. Well, it's a matrix, of course, but X, you could regard X as being this matrix with 1s, this nilpotent matrix. But that's just to express it neatly. Okay, now the next kind of monodromy data is Stokes data. So this is related to the irregular singular point at infinity. You have Stokes matrices. That's Stokes matrices. And from the point of view of analytic continuation, this is across sectors near, well, at infinity. Okay, so the Stokes phenomenon is that the behavior of the solution at infinity is different in different directions, on different sectors or different rays. And the numerical data which comes out of this, well, kind of interesting. It's the binomial coefficients, n plus 1. So I claim that the Stokes matrices, well, they are matrices, but you can extract the essential data, and it turns out to be binomial coefficients. Well, what are the binomial coefficients? Well, they are the coefficients of the binomial. Right, x. I could write x. I mean, as a formal variable. So the Stokes data, the Stokes matrices, are the crucial numerical data is actually just these binomial coefficients. It's kind of interesting. And then there's a thing called the connection matrix. So the connection matrix also has to do with analytic continuation, but it's from one singular point to the other singular point, right? So the connection matrix connects solutions near zero with solutions near infinity. And this is where the gamma class comes from. So the numerical data which is extracted from this is gamma 1 plus x to the power n plus 1. So I will talk about this in detail later, but gamma is the gamma function, 1 plus x. Well, you can take if x was a real or complex variable, you could take the Taylor expansion and then you get powers of x. But of course, the powers of x terminate. So x to the n plus 1 is actually 0. So although this looks like a Taylor series infinite, it's actually just a polynomial. So you get some coefficients. And again, the coefficients, as in this case, they are the numerical information. So this is very curious, perhaps, but anyway, this is what I will talk about. Now, if you know something about differential equations, you might be a bit surprised by how simple these formulas are, because usually this kind of data is very complicated. Well, monodromy may be relatively easy, but Stokes matrices are usually very complicated things, and the entries of the matrices are usually not integers. But in this case, they're all integers. They're binomial coefficients. So that's curious, right? I mean, if you take other well-known differential equations like the Bessel equation or the hypergeometric equation, you'll never get integers for the monodromy data. You never get integers. I mean, of course, you can rescale the coefficients to make things nicer, but you'll never get them all to be integers. But in this case, the Stokes data is completely integral. So something interesting is happening there. Well, also, of course, it's interesting because it's topological. All of this data I've written is purely expressed in terms of the cohomology. It's topological. So that's another interesting. So clearly, this kind of equation is special. Something interesting is going on. Yeah.
So why you have a 2 pi again?
No, it's not important. Well, I'm dealing with complex numbers, right? 2 pi I always shows up. Well, you can, well, okay, well, a simple answer to your question, because of the logarithm, log q. The monodromy of log q contains 2 pi I, right? So that's a kind of simple answer. But yeah, but of course, I don't have any 2 pi I here or here, do I? So it's a reasonable question. Why do I have here and not here? Well, that I don't have a simple answer. Yeah, I'll leave that chart there because it's kind of interesting to look at. So the de Broglie conjecture is, let me just say that the idea of the de Broglie conjecture, the geometrical interpretation of the gamma class, is, well, very roughly that the Stokes matrices, well, let's say one Stokes matrix is somehow related to the Euler form of the K-theory of X. And the connection matrix, so that's the central connection matrix, is somehow related to something called a helix. It has to do with exceptional collections. in the derived category of coherent sheaves, or in Kx basically. So in the case of x equals Cpn, this exceptional collection, so there are various choices, but one suitable choice would be just the standard line bundles. This is a sequence of line bundles. And so the Euler form, of course, is going to be the matrix of this with respect to this. The matrix of the Euler form with respect to these classes in Kx will be triangular because it's hom from OI to OJ. And the Stokes matrices, classically, they are always triangular. So there are some superficial similarities, but of course there are much more deeper reasons to have this kind of correspondence. Both sides have a braid group action. There's a braid group action on Stokes matrices. There's a braid group action on exceptional collection, and these seem to correspond. And this has something to do with homological mirror symmetry. Actually, references for this, well, I mentioned the Kontsevich article at the ICM 94, but there's a nice article by Zeslav in Communications Mathematical Physics in 1996, where he explains this in more physical terms, has to do with supersymmetric quantum field theories. And actually, he uses the TT star equations, the topological, anti-topological fusion equations, not the quantum differential equation. And I'll talk about that later in the next lecture, probably. So I want to explain how this monodromy data, especially the connection matrix, comes to be organized in such a nice way. That's what I want to try to explain. Okay, so let's get to more practical things. Let's go back to the quantum differential equation of CPN. And if you study quantum cohomology, you undoubtedly know Giventhal's work, which was reported in the International Congress article, 1994, where he basically put differential equations into the story, and that's what I'll tell you next. So Giventhal's solution of the quantum differential equation. So this is commonly known as the J function, or the I function, which is equal to the I function in this case. And this function is the following expression. It's a series expansion of a solution. So Q to the 1 over lambda x plus d. D is an integer, non-negative integer. Yeah, I'm keeping lambda for the moment, but I will put lambda equals 1 shortly. So what does this notation mean? Well, so this is, of course, the solution to the quantum differential equation by the Frobenius method. And this slightly strange notation. Well, Q to the D is Q to the D, but this means E to the 1 over lambda log Q x. Yeah, so that's where the 2 pi I comes from. This is the notation used here. So if you expand this, you see it's actually a polynomial in x, because x to the n plus 1 is 0. So let me write it as J0. It will be simply a polynomial like that. And the j's are then, so individually the j's are solutions of the scalar equation. So this, in fact, gives you a basis of solutions. So the matrix, the vector equation, n by n plus 1 by n plus 1. So the dimension of the solution space is n plus 1. But the nice thing is that we can regard this as cohomology valued. So it belongs to, it's a cohomology valued solution of the equation. That's what we think of. Yes, so now I will put lambda equals 1, because I won't need to use it today. So this is a convergent series to 0. So this is related to the monodromy, and of course that's where the e to the 2 pi I x comes from. So that's a very nice kind of reformulation of the Frobenius solution as a cohomology valued solution. Now 0 is not so bad because it's a regular singular point, but what happens at infinity? This is a different matter. Yeah, so I wrote a book about quantum cohomology, a kind of elementary explanation about 20 years ago, well, slightly less. And I completely ignored this because I didn't know it. I didn't know anything about irregular singularities at that time. And there was plenty to say about 0. 0 was actually kind of interesting. Well, this is to do with Gromov-Witten invariance, gravitational invariance, so there's plenty of things to say there. And of course, integral systems come into this story. Anyway, what happens at q equals infinity? Well, there's a naive approach to this question. By Galkin, Kolishev, Zagier, where they basically the statement is that the limit at infinity exists of something. So the limit as q goes to infinity of any, well, of the whole series, I mean the whole polynomial, so any ji divided by J0, let's say the first one, J0, exists. Well, for CPN, but more generally for other things. And they call this the principal asymptotic class. The principal, so it's a class, it's a cohomology class, right? And I call it naive because it's kind of easy to write the formula. I hope they don't mind me describing it as naive, but it's naive in the good sense. It's a kind of straightforward and meaningful. The question is, why does the limit exist? It's maybe not completely obvious. Usually when you take the limit of, well, of course, individually, J will go to infinity, right? But this will also go to infinity. So there's a possibility that something exists. And this is, okay, that's a statement. The limit exists. That's what they said. So this is interesting because it tells you some relation between what happens at infinity and what happens at 0. And it's also good because you can actually try to verify this numerically using computers. You can just calculate, for large values of q what happens, and you will find it converges. And if you're a number theorist, well, I guess they are mainly number theorists. So then you might be excited when you recognize some number as a value of the Riemann zeta function, you might think, well, there's something interesting here. And that's what they did. So,
excuse me, very simple question here. Near infinity, the Stokes matrix, I mean the asymptotic expansion we have to make up.
yes.
This really doesn't.
No. That's right. So it depends on the direction, of course, yes. So this will, it depends. The answer will depend on the direction of approach. And it will be different, right? It will be different from different directions. So you can see that there are of course, some problems with this. I mean, just to say that is not enough. You have to say more to justify this and to understand it. But anyway, there's a key question here which they are addressing. And the key question is, this is analytic continuation. That's the question. I mean, to understand how to deal with, how to treat, how to understand analytic continuation. Right? This is absolutely key question, and this is giving some information about that. Okay, so let me try to explain this a little bit. So why does the limit exist? Of course, this series converges everywhere. It's not just convergent near zero. It actually converges everywhere, right? But the convergence probably very slow near infinity. But still, using computers, you can try to estimate the limit. Okay, well, we need a little bit of ODE theory. So some ODE theory. Of irregular single points. So there's a theorem which I'm stating rather imprecisely, but I will be more precise soon. So consider the ODE. Okay, I'm going to write it like this. So this notation, psi is a function of a complex variable z taking values in GL and C. Z is complex. And what else? That's all. And then A is going to be a function of Z. So A is actually going to be, well, I'm only going to consider the case of a pole of order 2, because that's what I would need. And then the AI are constants. But it might be a finite polynomial, or it might be a convergent Lorentz series. So consider something like this. And let us assume that eigenvalues, so assume that the leading coefficient has distinct eigenvalues. Yes, call them A0 up to AN. Let's assume that. Well, then the theorem is that, first of all, there exists, well, essentially unique formal solution. Perhaps better to call it a normalized formal solution. So you have to make some choices, which I will call psi f. So psi is a matrix-valued, holomorphic matrix-valued function. And we can get a series Right, so in this, so now my notation changes from Q to Z, because I will try to use Z when I'm talking about general properties of differential equations, not necessarily quantum, but later on Z, Z equals Q will be a special case. So the singular point is a 0, pole of order 2. And we get well, you can't just get a Taylor series. You need an exponential factor, and the appropriate thing to choose is this. So there will be a formal solution in general like this. So there has to be an exponential. So basically, when you differentiate this, you'll get minus, you'll get 1 over z squared. I mean, that has to do with the squares, right? There's 1 over z here. So there's a normalized fundamental. Well, I'm assuming that there is no formal monodromy in this case. But I won't say any more about that. And then secondly, there exists, so part 2 of the theorem is that there exists a unique holomorphic solution. So, this is famously not convergent. So when you have a pole of order 2 or more, and you use the Frobenius method like this, you will not get a convergent series in general, but you'll get a formal series. However, there exists a holomorphic solution, which I will call psi z, on any Stokes sector. Let's call it omega. So if you restrict to a sector, you will get a holomorphic solution such that the solution is asymptotic to the formal solution as z goes to 0 within the sector in omega. Okay, so the theorem is such that psi is determined by its asymptotics on a sector. But of course, when you take a different sector, you get different solution. Although the asymptotics will always be the same. The formal solution doesn't change, but the holomorphic solution depends on the sector. So this is a well-known theorem, which is due to many people. Well, Stokes, I suppose. Well, maybe he didn't prove a theorem, but Stokes, Poincaré, Birkhoff, and then much later, people like Fukuhara and Turitin and Waseda, and then more modern versions of this theory were developed. But anyway, let's just think about this rough kind of version of the theorem. And of course, what I want to do is I want to take my psi to be, I want to take the quantum differential equation, and then I want to take psi to be the matrix constructed like this. So I put Givental's solution on the top row, and then you differentiate these functions and you fill up the matrix, and that's how you get a matrix fundamental solution. So I'm now taking my quantum differential equation to be this. Actually, it's not this. So I'm cheating. The quantum differential equation does not have distinct eigenvalues of the residue, but let's just pretend that it does. So I take my psi to be this, and then I can say from this theorem, thus. So by the theorem, well, assuming that the theorem applied to the quantum differential equation, which it doesn't really, but anyway, there exists some other solutions, not these Givental solutions. There are other solutions of the scalar equation. So y equals, well, I will call them G0. Gn, such that, so you see there will be another fundamental matrix like this, G0, Gn. You differentiate these. This will be psi another, okay, another one, another psi, and these have because of the form of because of this asymptotics and this. series, then the solutions will satisfy minus AI divided by Z in omega. Okay. So that's the that is our situation. So now let's apply this to our example. Well, let's take the 3x3 case because I can easily write that on the blackboard. So CP2, that means n equals 2, 3x3 case. Well, we can write. Okay, so the top line J0, J1, J2. I mean, we can write these as a linear combination of the other solutions. So in matrix form, I could write it like this. And this matrix I will call in the traditional way C00, C01. For some constants, Ci. Right, because they are both solutions, they are both bases of solutions of the same equation. So now what happens when we look at the quotient of two such things? So let's take, for example, J1 divided by J0. Well, J0 divided by J0 is not interesting, but so the first one is J1. So this will be, yes, well, it will be C01. Try not to make any mistake. That, right, so we have such a formula. So I want the limit of this to exist when q goes to infinity, when z goes to 0. Well, I mean q. So and now I'm really thinking about quantum differential equations. So when q goes to 0 on a ray in a sector, well, sector. I mean, because I want to consider a Stokes sector. Let's consider omega, Stokes sector. So then what happens? Well, yes, it doesn't look like it approaches the limit, but of course it does because, well, it has a chance to because we have this information. So this is, z goes to 0. So in the quantum differential equation, that means q goes to infinity. Yeah, sorry, very, very important, infinity. Q goes to infinity, we get these exponents showing up. And so let me write down the answer. So the answer is, it'll be ck1 over ck0 if gk is dominant on that sector, omega. So there are three eigenvalues, right? A0, A1, A2, and I'm assuming they're distinct. Well, maybe I'm assuming the real parts are distinct. Anyway, only one of these three will be dominant, and that means that's the only one that counts. So if k is equal to 2, for example, then this will be the dominant one. So you divide by G2, and then all of these things will just go to 0, and you're left with C2, 1 divided by C2, 0. So it's correct that it will converge to a constant. And that's the reason you can do this. That's the reason the asymptotic class exists, because it depends on which Stokes sector. And I suppose usually they would take a sector containing the real line or something, standard. and then you'll get an answer, and that will be the asymptotic class. So this is, well, this is maybe not a very useful form because you're just getting some numbers, right? I mean, you want to organize the information a bit better than that, but still, you get some numbers, and if you plug the given tile solution into a computer, that's why the limit will exist. Okay, but of course the point really is that, well, the interesting thing is that although we have a series solution at 0, the given tile solution, but that's not so useful to calculate the limit because it converges very slowly at infinity. And we also have a formal solution, right? So we have a formal solution which doesn't converge at all. But the interesting thing is that we can extract some information out of these power series. And of course, this is the idea of ODE theory. So there's a big theory of resurgence where you don't think about differential equations, you just think about a power series and try to extract some information from that. And there's a big theory of such things. So there's a big theory which can be used. Now, the way I explain this is not correct because the quantum difference equation is not actually of this type. So we have to be a bit more systematic. So let's perhaps just start again. So the first problem is that the quantum differential equation is not suitable for applying this theory. Okay, maybe I can erase that too. Does anybody have any questions? Right, so we want to do something more systematic. What's the time? Okay, well, first of all, we have to do something to the differential equation. Well, the first step is going to be transform the quantum differential equation to another form, to a good form. And the second step will be to apply ODE theory properly. I mean, rigorously. So the previous version was not so rigorous. So here we go. So the first step, lemma, the quantum differential equation for CP2 is equivalent to another differential equation, namely chi zeta I'm just doing the 3x3 case because it's easy to write on the boards. Chi. So here I have this matrix, here I have this. All the other entries are 0. So I'm changing the variable q from to a new variable zeta. And actually the definition of q is, well, definition of zeta, sorry, is, I'm going to take, there are various ways to do this, but I will take q to the minus 1 over 3. And then I will also do a small gauge transformation of the equation. So I replace y, the vector function y, by capital X, right? So I change the variable q to zeta, and I change the variable, I change the vector function y to x. And
How about the subscript?
this one?
Yeah.
Oh yeah, this is just d chi by d zeta. Yeah. Yeah, simply. Yeah. Yeah, so you can check that. So the A is a constant, so I'm not going to write it explicitly. It's something to do with 3, right? There are 3's all over the place. Anyway, you can check that works. And now we're in a quite different situation. We're now in a good situation because this differential equation, well, it has a pole of order 2. To 0, and it has a pole, a regular pole at infinity. But the important point is that the pole of order 2, see, the residue is that cyclic matrix, and the eigenvalues are, well, the cube roots of unity, or minus the cube roots of unity. So they are distinct. So this is a good equation to apply the general theory. And then the general theory, what does the general theory say? So let me make some definitions. Okay, well, what happens at 0, what happens at infinity, what happens in between? So first of all, what happens at 0? So I'm going to choose some sectors. So we define Stokes sectors. And I put a 0 to indicate that it's at 0. And they are a family, well, they differ by pi. And I start off with some particular, you have to start somewhere, so you take the sector. I mean, there's an official definition of Stokes sector, but I just tell you what it gives. So one Stokes sector is the 4 pi over 3 sector around the real line, and then you apply pi. So I'm really working in the universal cover here. I have to remember the angle. So they don't repeat periodically, they go round and round and round. And then we have a formal solution. We have a formal solution which I call psi or chi f. And it will be, well, it's similar to what I wrote down in the non-rigorous formula, but now it's rigorous. I mean, this can be proved. And again, it's the eigenvalues. Well, it's minus the eigenvalue. The eigenvalue minus the cube roots of unity. So actually, you get this. So omega 2 pi I over 3. Okay, so that's precisely what it is. There is a formal solution. And well, I can normalize it by making the first term the identity of the series. Because you can multiply by any constant matrix, still be a solution of the equation. And then we get holomorphic solutions on our Stokes sectors, but these are indexed by k. So therefore, I should use the notation chi 0 k for this, which has the property that it's asymptotic to chi f on the sector omega k. So we have that. And then we can define Stokes matrices. So Stokes matrices are defined by well, I could call it S0. Okay, I'll call it S0, okay. These are defined by the formula this is the definition of SK, because I have two different solutions, psi k plus 1, so they differ by a matrix. And we call our matrix SK. So that's what happens at 0. What happens at
in the definition of Stokes secretary, is it e to the minus pi r?
Yes.
You need k. Adjacent secretaries are related by
Pi.
I think if it's omega 1, then it's the k, but you already write omega k, so the k is not needed in power.
Oh, sorry, yes. I see what you mean. Yeah, sorry. Yeah, whether it's plus or minus is not important. I just decide to use minus. But yeah, they differ by pi. That's the point. Yeah, thank you. Okay, now the situation at infinity is much simpler because we do not have Stokes matrices at infinity. So what do we have? Well, we just have a series solution. So we have a solution which I will call psi infinity, chi infinity. These are chi. These are supposed to be all chi's. I'm really plagued by notation. You know, my zeta looks like 3, and my chi looks like psi. It's very difficult. Anyway, chi infinity is, there is a solution of this. So this is the sort of Giventhal type solution in general. This is a constant. Then zeta to the, so this is at infinity, so negative powers of zeta. And then here I have to put, well, the usual way to do it is something like this. So I put, so these numbers, these are matrices which depend on the equation. Actually, the suitable matrices are, for little m is this matrix, and for the script big M, it is a nilpotent matrix, which I will take to be -1, -1. Now, there's some choice here. This is not canonical. This is a choice of what they call the Levelt form of the solution. The Levelt form means you write it like this. So there is a solution, actually more than one, but I'll come back to that point a little later. And this is convergent, so this is convergence at infinity. Okay, and then finally we have what happens in between. These are the connection matrices. So zeta equals 0, related to zeta equals infinity, by a matrix which is defined in a similar way to the Stokes matrices. You define dk. So this is the definition of the connection matrices. So there are many connection matrices dk, and they are defined by this relation. So the solution which you've chosen at infinity is related to the solution you've chosen at 0. And this is called the connection matrix, the connection matrices. So there are infinitely many Stokes matrices and infinitely many connection matrices, but of course there are some relations between them, so they're not completely independent. I mean, they couldn't be, right? We're just considering an ODE which has a three-dimensional solution space, so there cannot be too many independent ones. Well, concerning the situation, let me just say as a preliminary theorem, this doesn't really make much sense, but it fits with my picture on the left. And the preliminary theorem is that the Stokes matrices are given by the binomial coefficients, and the decay are given by the gamma function class. So gamma 1 plus x cubed. So that means gamma of 1 plus x to the power 3. So I have to clarify given by. Well, I will do, but let me just say that in fact, if you actually calculate the Stokes matrices, which is possible. You see, this example is completely explicit. Completely, just a very simple differential equation, and one can compute everything exactly. So the answer, according to my calculation, is in fact this matrix. So, it's oversimplifying to say, so the binomial coefficients are 1, 3, 3, 1, right? Well, I don't exactly see that, but anyway, 3 is the important thing, because 6 is 3 squared minus 3. So, I mean, it's really 3. 3 is the essential point. And the connection matrix, well, in fact, D1 can be calculated also. So I will say more about this a bit later, probably the next lecture. But you can calculate it, and then the essential ingredient will be this gamma class. So I'm getting closer now to the specifics of the gamma class. But I'm not there yet. I'm still talking very roughly about what happens. Okay, well, one remark about these various matrices. I think I can write it here. There are various relations between these Stokes matrices and connection matrices. And what I can say in relation to, but what I want to say is that basically if you know the connection matrix, you can calculate the Stokes matrices. And if you know the Stokes matrices, you can calculate the Montgomery matrix. So the fundamental thing is the Stokes, is the connection matrix. So just as a remark, if you start with dk, you can produce sk, because sk is equal to this. Well, it follows from these formulas, right? And just think about the definition. You see it follows. So the Stokes is given by the connection. And then the monodromy, well, this is maybe not quite so immediate. Well, it's not immediate, but it's a fact. It's a fact that the monodromy of what? Well, monodromy is defined up to conjugacy, right? So monodromy of one of these particular solutions. So maybe psi k or psi k plus 1, I didn't write down. Well, maybe k. Anyway, I claim that it's equal to the inverse transpose. The inverse of the transpose there. So you see, you can get the monodromy, because we already knew the monodromy. We didn't need all this theory. And actually Stokes, there's a way to calculate that directly as well in this case. So I'm just drawing this sequence as a kind of conceptual companion to this, right? So somehow the most difficult one is the connection matrix. But there's actually a nice direct calculation of this. An algebraic calculation, which has been done by other people, but I would like to mention a paper by me and Nanko Ho, who is here. So we give a very algebraic, Lie theoretic way to do this. So the monodromy and the Stokes are actually computable algebraically, but the dk is not. Okay, so
just let me confirm the monodromy is the monodromy from the regular symmetry.
yes. Oh, well, no, I mean, no, sorry. So when I say monodromy here, I guess I mean monodromy. I think it's probably the monodromy of this. So this means at the irregular singular point, k or k plus 1, which is conjugate to the one over there. Yeah. So this will be conjugate to that. I guess we can check it, right? We take that 3 by 3 matrix, we multiply it by its transpose inverse, and then we show that it's conjugate to this. Yes, that should be possible. Yes, I didn't do it. Okay. Yeah. Are there any other questions? I actually went quite fast through that. A bit faster than I thought. So my plan is to start the second lecture now. Because the second lecture will be, I'm afraid, in danger of running over time. So it's good I started now. I still have 20 minutes. Okay, so yes, so this is the situation. So I want to somehow explain this more, well, concretely, but also more conceptually. So the title of my second lecture is, that was the phenomenon, right? So the title of the second lecture is Progress and Difficulties. Sounds ominous. Okay, lecture 2. So let's pretend we are starting next time. So again, I will start with history. So some history. Well, of course, there's been much excellent progress. So I'm going to make a kind of another diagram here. So I will write the author's name here, and I will write somehow the goal of the, well, first of all, this is history of a particular thing, right? The gamma class. Actually, only for CPM. So it's a very restricted history, but it's quite interesting. So the first thing I should say is that Professor Hosono and Borisov Horscher actually probably the first people who did this in the 1990s, but they were not considering phono manifolds. They were the goal, I think, of their work with the Calabi-Yau case. So I'll put this in parentheses because I'm only talking about CPN, right? But still, the idea, I think, came from Hosono originally. Now, there's a paper by Iritani, 2007, where his goal was perhaps to study the TT star structure of CP1. Well, and also he studied the toric varieties, but the TT star structure was only known to exist for CP1 at that time, and he made a detailed study of that. Around the same time, independently, I think Kontsevich and collaborators well, maybe a little bit later, they had quite a different goal. So they were considering what they call semi-infinite variations of Hot structure, or variations of semi-infinite Hot structure. And as part of that, they did the CPN example, gamma class. Then, as I already mentioned, Galkin, Golichev, Iritoni. Well, I mentioned Golichev and Galkin and Golichev. So these names are written in the abstract. I won't write it on the board. So Galkin, Golichev, Iritoni, 2014. They, well, they had, again, a different goal. I think their goal was to prove the Dubrovin conjecture in various cases. So as part of that, you have to calculate the gamma class. So they did. And then more recently, there was a paper by Cotti, Dubrovin, Guzzetti. Well, several papers, actually, starting at that time. Each group wrote several papers. They also had the goal of studying the Dubrovin conjecture. And actually, the gamma class for CPN was also studied by me at the same time. GIL, that means Gust, Itz, Alexander Itz, and Lin, Changshu Lin in Taiwan. And our work was actually done at TIMS, so I will add at TIMS. I think we did this between 13 and 15. So I often met Professor Wang. Sorry? Yes, in the old building, yes. So we met every time. And then we said, why don't we discuss quantum cohomology together in the future? But you were so busy and I was so busy, we never discussed it. now we have a chance to. Anyway, so we had a completely different goal. We were not trying to calculate the gamma class, although we did. We were interested in TT star Toder equations. So the Toder equations. And this actually includes the example of CP3. So we restricted ourselves to 4x4 matrices, and CP3 is one of those cases. So there are some difficulties so there's a lot of good progress, and of course after this there's much more progress. But well, you can already, I think, see there are some difficulties. So one difficulty is, well, actually you don't see this yet, you'll see it next time. But difficulty is that to actually calculate connection matrices, there's only one way to do it, and that method does not apply to general Fano manifolds. By no way. I mean, you can really only do things like projective space. Well, toric varieties are, of course, similar to projective space. You can do toric varieties, but you can't really get much further by this method. So this is one disadvantage. But, well, on the other hand, it's good to have concrete examples. Another problem, which you do see, I think, already, is that there are many choices involved. There are infinitely many Stokes matrices, connection matrices, and you have to somehow organize all this information. And well, one nice way to organize it is in the gamma class. That's a good thing about the gamma class. It organizes this complicated information. Also, maybe I should say that why are people writing papers about the Dubrovin conjecture close together? Well, the Dubrovin conjecture, as formulated by Dubrovin, the 1998 ICM, it was not very precisely stated. There were many ideas in that paper, and he stated something which later on people tried to make more precise. So the Dubrovin conjecture itself was not originally a very well-defined conjecture. It was a direction. So these are some of the initial difficulties. Okay, so I should finally tell you what the gamma class really is. I mean, I just wrote this formula, but what is the definition of the gamma class? Okay, well, the gamma class of a complex manifold. So let us, so X. Let's write the Chern roots of, well, the tangent bundle, right? So Tx. So the splitting principle, or various ways to define this. So we have some two-dimensional cohomology classes called Li. Then the gamma class of X is, so they call it gamma hat X. It's simply the product of gamma 1 plus Li. The i's. I mean, they're not necessarily, the number of Li's depends on the case, right? It's like you consider the stable tangent bundle. So it's n plus 1 in the case of CPN. And this is what it is. So this is a cohomology class in X. And because it's in cohomology, these gamma functions, because I should perhaps write down somewhere. That it's a well-known theorem of complex function theory that this, so Z is now a general complex variable. The Taylor expansion to 0 of this has a very beautiful form. Z, oh sorry, what am I? Z to the k, right? So this is the Riemann zeta function. Zeta k is the Riemann zeta function. So you see, it's when I have 1 plus Li, using this Taylor expansion, it's just a polynomial in X, or in Li. So in the case of CPN, let me see. Yeah, so for CPN, then we have the Chern roots are all the same. And there are n plus 1 of them. So therefore, the gamma class is gamma 1 plus x to the power n plus 1. And that's where that formula, where did I? Yes, that's correct, that's what I wrote, yes. Mm-hmm. So that's the definition of the gamma class. So using this series, for example, so n equals 2. I'll just write down so you can look at it. The gamma class of P2, CP2, is, well, you see, you have to cube this, right? So you get 3 gamma, and it's minus, so you get minus 3. Yeah, gamma is the Euler, this is the Euler constant, which is zeta 1, right? This is a Riemann zeta function of 1. So minus 3 gamma x plus 9 over 2 gamma squared plus pi squared over 18 x squared full stop. So it's just the cohomology class. So this is a class in, X is a generator of CP2, right? So this is in cohomology of CP2. Well, zeta 2, right? So the zeta 2 Riemann zeta function value is pi squared over 6. So that's where this comes from. So that's what we are talking about. Yes, well, you know, well, this might be a good place to stop, because next time I want to continue by looking more carefully at the differential equation, and well, trying to compute. No, I will basically compute the gamma class. And then I will talk about the real structure and what kind of effect it might have. Yeah, so it's a little early, but I think I'll stop here.
Is there any occasion you will use this gamma class because you put a hat there? So will you treat it as a differential operator? You actually quantize the term.
No, I will not do that. maybe.
So far we didn't.
No, I don't think so. I don't think so.
So then why people put hat?
I don't know.
I think you think the hat is some kind of quantization.
Yes, I told you I'm not a specialist. But of course, the quantum, if we consider the quantum D module instead of quantum cohomology, yes, would be very reasonable, right? I mean, why not? Why not put differential operators?
I just think that seems to be quite reasonable to appeal.
Yes, yeah, the quantization in the sense of quantum D module, yes. But no, I don't think I saw anyone doing that, but.
Somehow related question is that very naive. For arbitrary complex vector boundary, we can define normal class.
Yeah.
Why tangent boundary?
Yes, for any, that's right, for any complex vector bundle, yes.
So, tangent boundary is special, right? So that's related to somehow quantum component.
Right, exactly, yes. Yeah, so of course they say that, this is an example of Hertzsprung's genera, Hertzsprung's, multiplicative cobordism invariant. So the gamma sequence is an example of Hertzsprung's general construction, which would work, yes. Well, yes, which would work for any bundle.
Then let's start speaker again.